Anyway, welcome back. I apologize for starting a little bit late today. It looks like we have a relatively small class today, which makes sense because if people have already taken algebraic topology, then a lot of this is review. But today we'll be talking about simplicial homology. So what did we do? Let's do a quick review before we get started. So what did we do last time? We defined chain complexes, and we also defined chain complexes, and we barely defined simplicial homology. Though we sort of just wrote down a definition at the very end and didn't really take much time to explain everything. So today I'm going to review that a little bit and then give examples of how you actually compute these simplicial homologies. So last time we defined them as a quotient group, right? So as a quotient group between the cycle group and the boundary group. And that's basically what they are, but let's see. So if we write down some notation, so today we're going to be computing simplicial homologies. And we're going to do it once from the definition, and another time we're going to show how we can make use of some linear algebraic techniques to more quickly compute to compute Betti numbers. Okay, so what did we have? So we had K, which was a simplicial complex. So this might have arisen from a check complex or a return strips complex or whatever, but we have some simplicial complex, so a collection of simplices. And we have CP, which is CP of K. So we're all going to be working over the same simplicial complex all the time now. So I'm just going to drop the K. So this is going to be the group of P chains. P chains. So C is equal to the sum over AI sigma I, where sigma I are in K P simplices. And the AI are going to be, we're going to be only working over the finite field of order 2. So as a couple people were mentioning last time, normally you have to do these alternating sums of plus or minuses, but since plus or minus 1 are the same in the finite field of order 2, we don't need to worry about any of that, which makes a lot of the theorems a little bit easier and a lot of the computations easier to do. And importantly, we defined a boundary operator, BP, which goes from the group of P chains to the group of CP minus 1 chains. And this is the boundary homomorphism. So for each simplex, this is just getting, for each p-dimensional simplex, this gets you the sum of all the p minus 1 dimensional simplex bases. Boundary homomorphism. And this gives rise to a chain complex. So let's look something like we have the p plus 2 going to c plus 1, the p plus 1 going to cp, the p going to cp minus 1, and so on. And importantly, we have this boundary homomorphism, and we can look at these homomorphisms, these DPs, and we can look at their image and their kernel. So we're going to let ZP, sorry, I keep on messing that up, ZP, which really is ZP of K, but we're just going to call it ZP, and this is going to be equal to the kernel of DP, and this is going to be the subgroup of P cycles. And we're going to let BP, which really is BP of K, that's going to be the image of DP plus 1. So this is the subgroup of P boundaries. And importantly, both of these are subgroups of CP, right? Because one is the image of some higher homomorphism that maps into it, and the other one is just the set of things that are in the kernel of the homomorphism and going from that space. So if I draw that a little bit more pictorially, so I have some, let's say this is CP plus 1, and then within that we have some smaller subgroup, which is ZP plus 1. And recall we had the fundamental lemma. So so our fundamental lemma, which stated that dp plus 1 of d is always equal to 0. And so what that implies is that bp plus 1 is a subgroup of zp plus 1. So we have this hierarchy of sizes. And if you write this out as a chain complex, this comes from dp plus 2, and then it goes in the next step over via dp plus 1 over into the same sort of thing. So here we have cp, ZP, Actually, let me draw that out a little bit more nicely. ZP and BP. Okay. And importantly, what's happening is everything that's in ZP plus 1, all of that maps down to 0, right? Because that's by definition. That is the kernel of DP. Sorry, this is DP plus 1. And so that all that maps down. And everything within C plus P plus 1, all of that maps down into BP, since that's a subgroup of P boundaries. And of course, this continues. So this can map via DP into CP minus 1, and you have the same sort of relationship. Okay, so that's sort of pictorially what's happening. And in every step of the boundary, you're mapping a bunch of stuff to 0, some stuff remains, etc. And now what we did is, so let me recall the definition of the P homology group. The P homology group is HP, which is equal to ZP modulo BP. And the Pth Betti number, beta P is equal to the rank of the P homology group. So the rank of the group is, of course, the smallest cardinality of a generating set. Here. And we'll go over that again in a moment. So, but now let's recall that, so this is all review of basic algebra. For C in ZP, the cosets C plus BP form HP. So those are the elements of HP. Okay, so standard quotient group stuff. And of course, we can define the cosets. The cosets of HP are homology class. A homology class and we also know that and we can call any C1, C2 in C plus BP are homologous. And you may see that denoted C1 squiggle C2. And let's just recall a couple other things in case this is useful. So the cardinality of a group is its order. The cardinality of a group is its order. Oh. So if we have something like CP, which is equal to this is generated by all the P simplices, right? So sigma 1, sigma 2 through sigma n, where our sigma I are in K are P simplices. Well, that implies that the order of CP is equal to the size number of elements in CP, which is of course just 2 to the n. Because we're working over the finite field of with just 2 elements, so each of these, you can think of each element of CP as just asking whether a particular simplex is present or not. Now, if you're working in a field of a different, well, in a different field, this would not be the case. But life is easy when you're working in the finite field of order 2, which is why we do that. And note that this also is nice sometimes for computations, because CP is then isomorphic to the group of bit vectors. The group of bit vectors under the XOR operation. Okay, so this is we are going to be worrying about computation, and it turns out this makes things easier to compute. And so if you take in topology, you'll know that the homologies, oh, sorry, there's a chat message. Let me see what that was. Oh, I thought there was a chat message, maybe not. Anyway, yeah. And I recall that the rank of a vector space, or group in this case, but is just its dimension. So the rank of CP is just equal to n. And it's also the size of the minimal generating set. But we have a couple useful facts. So the Pth Betti number, which is equal to the rank of HP, you can also think of that as just log 2 of the size of the total number of elements in it, which is of course also equal to log 2 of the size of ZP divided by VP, which is also equal to the rank of ZP minus the rank of BP. Okay, so all these things like add together in the natural way. Let's give a quick example. So if we let K be a triangulation of, let's say, I'm going to make this a weird b to the k to refer to a ball. So let's say this is a ball in Rk, where the size of this is less than or equal to 1. Okay, so it's just the unit ball. Then it turns out that HP of k is equal to just the 0 set for all p not equal to 0 and beta naught is equal to 1. Okay, so this is kind of hard to prove. So this is a non-trivial thing to prove that you would prove in a topology class. We're going to consider something simpler today in this class. So we're going to consider the simpler thing of, well, what about the homologies of just a simple tetrahedron, or by a single K simplex? Okay, and we're going to explicitly compute that, and then we're going to show a general way of computing that using some linear algebra, using Smith normal form. So let's do something simpler. So simpler, we'll let K be the faces of a single K simplex. K simplex sigma K. So I say the faces of it because I'm including the K simplex itself, as well as all of its faces. So you can think of this as a high-dimensional tetrahedron or something like that. And our claim, which you should expect because you might assume that the homology of a K simplex is the same as the homology of a K sphere, and you would be right. Our claim is that HP of K is equal to 0, just the 0 element. The group was just one element for all P not equal to 0, and beta naught is equal, the first Betti number is equal to 1. And let's actually take some time to prove this now. So let's prove this. Well, what does it mean for the HP to be the group with just the 0 element? Well, we know, oh, sorry, go on. Exactly, because if the quotient group ends up being 0, then that means that we need ZP to be equal to BP. Okay, so that's all we need to prove in order to show that this is true. So we need to show that, effectively, we need to show that all the P boundaries are also P cycles. And of course, we know that in one direction, right? Because we know that any P boundary, when you map it again, is going to go to 0. But what we need to show is that that includes all of, that's all of the cases for a P cycle. So let's let the set U naught through UK be the set of vertices of this K simplex of sigma K. Okay, so now what we're going to do is we're going to start by considering, let's put this in purple, I guess. So note that CK is equal to the set 0 if we sigma K, and CK plus 1 is equal to the set with just the 0 element, right? Because of course CK is generated by sigma K, since that's the only K chain we have, K simplex we have. So we know this is true, and that immediately implies that BK is equal to 0, because the image of 0 under the boundary operator is of course going to be 0, because the image of 0 is always 0, and therefore we know that the sigma K, which is equal to the sum over J equal to 0 to K of U naught all the way through, but not including UJ through UK, is not equal to 0 because each K simplex appears exactly once. Okay, so then this implies that sigma K is not in ZK. okay, because it doesn't map to 0. Which then implies that zk is just equal to 0, since that's the only other term left, which implies that hk is equal to 0. Okay, so this is for just the case of ck, so the highest dimensionality that we care about. So now let's consider the all the intermediate cases. Well, let's consider 0 less than p less than k, and then we'll let c be in zp be a p cycle with simplices of the form ui naught through uip. Okay, so now we're going to consider well, p cycles for p less than k, and so we picked some arbitrary p cycle, and each of its simplices has this particular form, right? And they might have different. I mean, of course, they have different vertices, but each of them has. You can write out as well p different vertices because it's p there, because each of the simplices is a p simplex. Now that we do that, we can define another set. So let D be the set of all p plus 1 simplices of the form u naught ui naught through uip. Okay, where we're picking some a vertex u naught, and we're adding it to all the simplices that are. So we're adding it to all the simplices that are in C. But sometimes if u naught's already in there, then it won't become a p plus 1 simplex. You just get the same p simplex back, right? So if u naught is already in the simplex of C, then there isn't a corresponding p plus 1 simplex. But when you add u naught to a simplex that doesn't already have it, well, then you get a p plus 1 simplex, right? So now we can also view D as a p plus 1 chain. Rather than just as a set. This is one of the niceties of working with the finite field of order 2, is because you can just view the set as the sum of all the elements in the set. And so we can view this as a p plus 1 chain rather than just the set. And now we can claim a couple of things. So our claim is that the boundary of D is equal to C. So this sort of makes sense, right? Because what we're saying is that we've generated the C out of like adding stuff over to D. And now our claim is that, well, the boundary of that thing is C. But note that C here is just anything in the ZP. So anything in the cycle group. So if we can show that this is true, then that would prove our claim that ZP is equal to BP. Okay, so now let's prove this. And this proof will be in a bunch of different cases. So let's start in case A1. So we're going to consider, so we're going to consider a P simplex, tau in C, where U naught is not in tau. Okay? So if U naught is not in tau, then there is a corresponding P plus 1 simplex, right? When in D, because we add U naught to it. So when U naught appears exactly once as a face of U naught, UI naught through UIP, which we know to be in D by the construction of D, right? That's how we constructed D, as we did all those things. But it appears only once because yeah. So this means that tau appears exactly once in row D. Or sorry, in DD. Okay, so if tau is in C, then tau also appears in the boundary of D exactly once. And the exactly once is important because if it appeared twice, then they cancel out. And so you need an odd number. Well, let's go into case 1b. Consider a P simplex, tau in C, where U naught is in tau. Okay? So U naught's in tau. We're still going to add U naught to it, but when we add U naught to tau, nothing happens because U naught's already there. And so therefore, the corresponding P+1 simplex is not actually in D. And so we can't use that same line of argument. But we can use a slightly different line of argument. So what we're going to do is we're going to let sigma be the P-1 simplex formed by dropping tau. By dropping U naught from tau. Okay, so instead of going up one step, we're going to go down one step and say that, well, let's let sigma be some P+1 simplex. And we know that sigma appears an even number of times in DC as C is in the cycle group, right? So if it appeared an odd number of times, well, then it would then C wouldn't be in the cycle group, and so therefore, So
we need that to cancel out.
Yeah, exactly. So you need it to appear an even number of times. Well, then this implies that an even number of P simplices in C contain sigma, right? Because when you're taking the boundary, you're like you're dropping one. You can think of taking the boundary as taking each of your simplexes and summing together, dropping one term from each of your simplexes. So now, if a P simplex contains both U naught and sigma, well, if a P simplex contains both U naught and sigma, what can you say about that P simplex? Well, not only is it in tau, it is exactly tau. Tau is precisely the P simplex that has U naught and sigma, right? Remember, we generated sigma by dropping U naught from tau. So all other P simplices containing sigma, therefore have a corresponding P+1 simplex in D, right? Because all the other simplices don't have a U naught, and therefore they have some corresponding thing in D, because you add U naught to them, which implies that you have an odd number of P+1 simplices in D that give rise to tau under the boundary operator. But if you have an odd number there, then that means that tau appears an odd number of times in DD. And of course, it appears an odd number of times in DD, that means tau is in DD. And so regardless, even though we picked out this vertex U naught in our argument, it doesn't actually matter whether it's present or not. A P simplex that's in C is also in DD. Okay, but now we need to prove it the other way, right? So if it's not in C, then we have to prove that it's not in DD. So let's go to case 2a. So case 2a here is we're going to consider a P simplex, tau that is not in C, where U naught is in tau. Okay, and we just need to show that this also doesn't appear in DD. And the argument's actually going to be exactly the same as our previous argument. So we're going to, again, let sigma be the P-1 simplex formed as above by dropping U naught from tau. And of course, our logic above showed that there are an even number of P simplices in C contain sigma, right? But now note that none of these p simplices, but none of them contain both u naught and sigma, because tau is not in sigma. And as you just said, these p simplex containing u naught and sigma is exactly tau. Which means that, well, all of them have corresponding p+1 simplex in B. But there are an even number of them, right? So this implies that tau appears an even number of times in DD. Okay, and if it appears an even number of times, that means it doesn't appear, so that proves this case. And lastly, we have case 2b, which is just that, well, if you consider a p simplex, tau, which is not in C, where u naught is not in tau. This argument's slightly different, but it's still fairly straightforward. So in order for tau to be in DD, there must exist some vertex, u prime, such that u prime tau is in D, right? Well, that's just by definition. But of course, we know that u prime is not equal to u naught, because otherwise we'd have u naught tau is in D, which would imply that tau is in C by the construction of D. So that can't be the case. So that would be a contradiction. So contradiction. So we know that this is true. But on the other hand, we know that if we have u prime is not equal to u naught, then u naught is not going to be in u prime tau, which is in D, right? But this also contradicts the construction of D, contradicts the construction of D. And so both of these contradict the construction of D, and therefore we know that tau must not be in DD. So if you suppose that tau were in DD, then that would be the case. And that completes this proof. So together, all these things together imply that DD is equal to C. Okay, and that implies that hence ZP is contained in BP, which implies that ZP is equal to BP for 0 less than P less than K. Okay, now we only have one case left, right? So we've now shown that it's these things are equal for everything greater than 0. And note that we did need to make use of the fact that this was greater than, we made use of a couple of different facts here. One of them that was important is that we made use of the fact here that that this is actually just a simplex, because we made use of the fact that otherwise that might not be in C P+1, right? So this is where we made use of fact that sigma k is a simplex, right? Because otherwise it might, like, you might have some face that wouldn't be part of your chain. Okay, so now let's look at the case where P is equal to 0. So now we're going to consider now P is equal to 0. And note that the boundary of any vertex is 0. So we know that Z0 is equal to C0. And therefore, the size of Z0 is just equal to 2 to the k plus 1. but where that's the number of vertices, because that's the number of vertices we have in the K simplex. So now suppose we have a zero cycle, C, which is equal to UI1 plus dot 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 plus UIL. If L is even, can pair off vertices to form D in C1 such that DD is equal to C. And so this implies that C is in B0 if L is even. That all right? So basically, if you have some set of points, if they're even, you can just create something like that. And that's going to be in your boundary set, because that's good. It's going to be the boundary of that thing. But if it's odd, you can't do that. So if L is odd, L odd cannot. So C is not in B not. And so therefore, it turns out that this is exactly half of the cases for each case. So the number of things in B naught is equal to the number of things in C naught divided by 2, which implies that the size of H naught is equal to the size of Z naught divided by the size of B naught, which is equal to 2, which implies that H naught is homomorphic to the finite field of order 2, the finite group of order 2, which implies that beta 0 is equal to 1. And that completes the proof of this. So I will mention here that I have just been talking about unreduced homologies. It is also possible to define reduced homologies, because right now it's a little bit weird, right? So if you think of homologies as like high dimensional holes, why are we saying that the zeroth homology is 1 as opposed to 0? And the answer is we're somehow looking at connected components, not at holes. And for convenience, it is possible to define a reduced homology that actually counts holes rather than including connected components in the zeroth homology. But we're not going to worry about that. So instead, we're going to make use of, talk about a couple of things we can do with these Betti numbers and these homologies, these simplicial homologies. The first thing I'm going to do is let's talk a little about the Euler characteristic. And I am running out of time, but I always run out of time. So you may be familiar with the Euler characteristic from study of like Platonic solids or things like that. So the Euler characteristic of a simplicial complex. So complex K is the alternating sum of the number of p simplices. Alternating sum of number of p simplices in K. And so chi is equal to n0 minus n1 plus n2 minus n3 plus n4 dot dot dot, where ni is equal to the rank of ci in your simplex, right? So because that's just the number of simplices you have, number of I simplices or p simplices or whatever. And you may have seen this in a slightly different form in 3 dimensions, where you called the Euler characteristic to be equal to the number of vertices minus the number of edges plus the number of faces. So for a 3D solid, like that's something that you may have seen before. This is just a higher dimensional generalization of it as a characteristic of a simplicial complex. And let's give ourselves a little bit more notation to make life easier. So we're going to let lowercase zp be equal to the rank of, well, the cycle group, and lowercase bp to be equal to the rank of the boundary group. Then, of course, we have that np is equal to zp plus bp minus 1, right? So that's just the rank nullity theorem, effectively, for the map dp. So then you'll notice that chi is then equal to the sum over p greater than or equal to 0 of minus 1 to the p zp plus bp minus 1. And we're going to say that b minus 1 is equal to 0 for simplicity. Okay, and you can sort of understand this if you were to generalize things out as c naught is just equal to z naught. So things get trivial once you get down to 0. When you expand this out, this is going to be z0 plus b minus 1, and I'm just going to say that that's equal to 0, minus z1 minus b0 plus z2 plus b1 minus z3 minus b2 plus dot dot dot. And you notice that we compare this together in a slightly different way. Compare together the z0 and b0. We compare together the z1 and b1 and so on. And when we do that, this ends up being the sum over for p greater than or equal to 0 of minus 1 to the p times zp minus bp. But of course, that means that this is exactly just the alternating sum of the Betti numbers. So the alternating sum of the Betti numbers gives us precisely this generalization of the Euler characteristic. And I'm going to write down a fact that I'm not going to prove. So simplicial homology is independent of triangulation. Of a topological space. So it would take a little bit more work, but if you take a topology class, you might define something called a singular homology. That's really how like a topological space can be morphed via some sort of deformation. And simplicial homology is equivalent to this singular homology. This is beyond the scope of this course, but basically means that if you have some topological space and you triangulate it somehow, it doesn't actually matter what triangulation you pick, and you get the same simplicial homology, which brings us to the Euler-Poincaré theorem, which is that the Euler characteristic of a topological space, that is precisely the alternating sum of its Betti numbers. So somehow we can make use of a triangulation of a space to compute an invariant on the topological space itself. Okay, and this is a very beautiful fact about topology. We're not going to go into too much detail, but this is just an illustration of one of the ways you can use Betti numbers and why these things are important. But now, how do we actually compute a simplicial homology, right? So we went through a ton of logic to like compute the simplicial homology for a very simple object here, right? And that's not something we want the computer to be doing. So is there a quicker and easier way of computing these simplicial homologies? The answer is yes. And the way we do it is we just turn to linear algebra, since we can think of the boundary map operation as, well, a matrix. So for that, in order to compute these things, we're going to define a boundary matrix. Because of course, CP and CP minus 1, you can think of them as vector spaces over the field F2. And so then you can define a DP as a linear map from one space to the other space. And once you are defined as a linear map, then you just go back to standard algebra and you can define, well, you can just write it down as a matrix. And it turns out then all you have to do is in fact find the rank of the matrix. So let me be a little bit more precise there. So we're going to let K be a simplicial complex. And of course, in order to go from a linear map over into a matrix, you need to have some basis of both your starting and ending space. So we're going to index the p simplices x1 through x1 sub, x sub np. And this is going to be the basis for CP, right? And we're going to index the p minus 1 simplices y1 through yn p minus 1. That's just the number of y minus 1 simplices. And so note that these are bases for CP and CP minus 1 respectively. Well, then we can write out the function. So let's suppose we had some xj. Then this is just equal to the sum over I equal to 1 to n sub p minus 1 of some coefficient aj I times yi, where aj is equal to 1 if yi is a face of xj. So here the xj's are p simplices, and we know that aji is and we need aji is equal to 0 otherwise. Okay, so this encodes the math that we're doing with the boundary operation. And so then for any p chain, since of course now we can say stuff for all p simplices, so that defines it for any p chain. For any p chain, let's say C is equal to the sum over j equal 1 to np of, let's say, aj, xj. So we're reusing a, but like that has just one coefficient. We know that dp of C is equal to the matrix a11, a12 through a1 np down to a n minus np minus 1, 1, a np minus 1, 2, a np minus 1 np. Okay, just all the coefficients as you'd expect, times, of course, the vector, which corresponds to C in CP. And then the output of this is written in coordinates, of yi. And now we have a matrix. Well, it's a little bit more complicated to look at the rank of a matrix of this matrix than it was in like standard linear algebra over R or C because, well, we're in a different field here. And so we're going to use a slight generalization of row echelon form. Note first that the columns of this, I'm going to call this dp now a matrix. So of course, we've now identified it as a matrix. The columns span the image of dp as a usual column span, which is equal to bp minus 1. So the rank of dp is equal to bp minus 1. So all we need to do is compute the rank of this thing. And you'll recall that exchanging columns or adding one column to another doesn't change rank. And the same for rows. Okay, so that's just standard Gaussian elimination type stuff. And so we can do effectively a Gaussian elimination on the entire matrix. And we're going to do it in a very particular way. And this is going to be, we're going to define, so whenever you do these sorts of operations, you can think of that as left and right multiplication by matrices, right? So you can think of the Gaussian elimination by multiplication by some set of elementary matrices as you swap the rows or as you swap the columns on the other side. And so we're going to define something called Smith normal form. So for any matrix, not in the reals, any m by n matrix where R here is a principal ideal domain. So this is the Smith normal form is defined more generally for principal ideal domains. It's obviously defined for fields. We care about it mostly in the context of fields, but occasionally you'll care about this in other contexts. Where R is the principal ideal domain, there exists S in R to the m by m and P in R to the n by n invertible matrices such that SAT is equal to some matrix that has terms on the diagonal up to some point here and zeros everywhere else. And it turns alpha I divides alpha I plus 1 for 1 less than or equal to I less than R. So what does this look like? So this is the Smith normal form. What does this look like for a finite field of order 2? Well, in the finite field of order 2, there's only one non-zero entry, right? So that means that in our finite field of order 2, what ends up happening is you just get ones along the diagonal up to a point and then zeros everywhere else. And that tells you the rank of the matrix after you've done these Gaussian elimination steps, as you'd expect. And note that you can think of S and P as sort of change of bases in Rm and Rn, right? So that's exactly what they are. They're change of bases in our case, CP or CP minus 1. So originally our bases were the set of simplices. But now we're going to change the bases a little bit via these change of basis matrices that we get via Gaussian elimination. And then what we end up getting is, well, a different basis for all that. And our final form of this matrix, so in our case, for dp, that's going to be S dpt is going to be equal to some other matrix that has this shape, where we have some set of ones here. And this thing is going to have be the rank of, oh, sorry, this is going to be p minus 1. This entire thing is, of course, just going to be np minus 1, because that's the rank of cp minus 1. And this thing here is going to be np, because that's the rank of cp. And this here is going to be zp. Okay, so from the so once we've done the Smith normal form, we can read off the ranks of the boundary and cyclogroups. And it turns out that the Gaussian elimination takes around order np minus 1 times np times the minimum of np minus 1 and np, time and order np minus 1 plus np squared space. So it's cubic in time and quadratic in memory. Quadratic memory. Where this is cubic and quadratic in the number of simplices. This isn't great, but this is relatively efficient. And this is why we computing simplicial homologies is relatively easy. And often whenever you're doing this sort of topological data analysis, that's one of the easiest things there is to compute. It is worth noting that even the easiest thing to compute in some sense for topological data analysis is cubic or quadratic, which is bad by many data science standards, which is one of the reasons why you normally don't actually compute these for everything. And so like there's a reason why, oh, what just happened? Come on back. Oh, there, okay. But yeah, so this, and so for data sets though, this is still feasible. So our computers are fast enough to do this. And so what the people often do in practice is you generate a filtration of victorious Rips complexes by increasing radii, and then you use these methods to compute which homologies are persistent for the different victorious Rips complexes.
You need to do this like for different choices of the radii.
Naively, yes. There are more clever ways where you can take advantage of the shared knowledge. Yeah, which we're probably not going to get into in this class, but this, as you can see, this is a lot of buildup. But basically, this is sort of showing you how you can make use of just like very small finite fields in order to compute all these things quickly. And I should note that quickly, in this case, it's still slow compared to many other methods. Yeah. Okay, that's all for today. I will see you all next Wednesday. Bye.